In this video, I will give you an overview of our work on the formal foundation for symbolic evaluation with merging. And if you would like to learn more, check out our proper talk and our paper. Sober-aided tools such as verifiers or synthesizers work by reducing the problem into logical constraint solving. What's common in all of these tools is symbolic evaluation, which is a compilation process that transforms a program into its logical encoding. And the most important part is the symbolic evaluator for the host language H. In our work, we target the host language H to be the language call scheme extended by abort and error. And the reason is due to the expressivity of this language. Call scheme, being an extension of lambda calculus, allows you to use recursion and loop. Call scheme is also parameterized by primitive data types and operations, and so you can add your own. Abort and error, on the other hand, allows you to express assertion and assumption naturally. And so, you can write this kind of program with this language. So this is it. What we have is the new semantics for symbolic evaluation with merging. It is a combination of two existing approaches, symbolic execution and bounded model checking. We use merging from the bounded model checking to combat the path explosion that arises in symbolic execution. Now, the next question is, what does it mean for symbolic evaluation with merging to be correct? Keep in mind that our language has loop and is not known before how to reason with merging in presence of loop. The closest one is bounded model checking, but the correctness theorem of bounded model checking does not support loop. It requires that you unroll all loops away first. In our work, we detail what it means for symbolic evaluation with merging to be sound and complete with respect to the concrete evaluation. We determine several properties of our symbolic evaluator. These properties are desirable because the clients of our symbolic evaluator can utilize these properties to help with debugging. The first property is reducibility. And this one says that the symbolic evaluation will reduce us into concrete evaluation when our inputs are concrete, even in presence of loop. The second property is legality, and this one says that our symbolic state contains formulas that you can use to determine the presence of errors in that symbolic state. The last one is determinism, and this one says that if you run symbolic evaluation multiple times, the results will always be the same. We mechanize our framework in the Lean theorem prover and also implement a reference symbolic evaluator in Lean. We also implement an optimized symbolic evaluator in bracket as a new rosette system, rosette 4. And lastly, we check that both implementations agree with each other using differential testing. Evaluation shows that when compared the previous rosette system, rosette 3, against the new rosette system, rosette 4, with our new symbolic evaluation semantics, programs can utilize the expressiveness of rosette 4, leading to a simpler code and a more concise code. Evaluation also shows that when compared rosette 3 with rosette 4, rosette 4 has a performance that is as good as rosette 3, and sometimes is even better. That's it. This is the formal foundation for symbolic evaluation with merging. See you at Purple.